Hello, Saner 2021. Thank you so much for joining me. I'm Kaylea Champion, and the project I'm presenting was conducted together with Benjamin Mako Hill. We're part of the Community Data Science Collective, which brings together researchers from University of Washington, where I am, as well as a series of other places within academia and industry. The collective studies the dynamics of online communities, including open source software production communities. And I want to share our sincere appreciation for the Ford Sloan Digital Infrastructure Initiative that made this project possible. The Heartbleed vulnerability in 2014 affected the security of SSL traffic worldwide. Despite our global reliance on this package, at the time when Heartbleed was discovered, the development team for OpenSSL was only 4 volunteers. This event raised concerns that there may be other vital pieces of software acting as infrastructure, similarly neglected. This perspective, software as infrastructure, is laid out in Nadia Eghbal's report, Roads and Bridges. If you're interested in reading more about Heartbleed and the specific dynamics of how this vulnerability was tackled, I recommend James Walden's paper from the Mining Software Repositories Conference 2020 entitled The Impact of a Major Security Event on an Open Source Project, The Case of OpenSSL. OpenSSL is one of a vast range of free/Libre open source software or FLOSS projects like GNU Linux, Python, Firefox, and the Apache web server. These projects were developed largely by volunteers who select their own tasks and priorities. This can be an advantage. As Yochai Benkler points out in Wealth of Networks, individuals can very efficiently match their interests and skills to tasks. Networks allow for distributed effort, and version control tools allow all those contributions to then be combined. This efficiency gain may come with a substantial drawback, however, as FLOSS has grown in popularity and become infrastructure on which modern commerce and communications rely. What if the tasks that volunteers select are not the tasks most needed by the public? What if neglected infrastructure most in need of repair is invisible? How do you prioritize among the many crumbling roads to choose where to focus your attention? This project is part of our answer to this challenge. Our insight into this is derived from a basic expectation of infrastructure. We all might hope that the most important components of software infrastructure, those bridges we drive over most often, are also the ones with the highest quality. But how do you detect cracks in virtual cement? How do you detect at-risk infrastructure components before they cause major failure? This sketch shows how we might think about that relationship between quality and importance. In those cases where importance meets quality, we would call that software component aligned. The supply, in terms of quality, meets the demand in terms of importance. But that alignment is often not the case. Infrastructure can be misaligned. When quality is high but importance is low, we would call that overproduction, not a problem other than the potential for wasted effort. Alignment indicates a match between quality and importance. This is the ideal case because the quality meets the importance of the software. And we have a particular concern for software falling to the right of this diagonal, where heavily used components are relatively low quality, and that's a problem. We developed a 5-part approach for identifying underproduction. I'm going to walk you through the steps and then describe an implementation of this general method to a specific case. So, step 1, identify a body of digital infrastructure that you can compare. Step 2, identify a measure of quality that you think reflects something important about the software. Step 3, identify a measure of importance that you think is significant in your context. Step 4, specify a relationship between quality and importance. What is that ideal relationship between them? It may vary depending on your location, depending on your context. Step 5, test for deviations to find relative underproduction. So that's our 5-step method for measuring underproduction. And we took this general method and then applied it. I'm going to walk you through what that looks like. For step 1, we applied our method to the Debian project. This is a valuable site for study in its own right, since Debian forms the backbone of Linux web serving worldwide and gives us a very broad view. We extracted data from Debian's public repositories for this analysis, including their bug tracking system and release databases. For our measure of quality, we use speed of problem resolution extracted from bug reports. However, measuring bug resolution time requires some specific handling. At any given moment, many bugs are open. New bugs are being reported. And if what we care about is how long it takes to fix them, we don't want to drop those that are still open because they have a lot to contribute to our understanding. So one strategy is to borrow a method from biostatistics and conduct a survival analysis. This plot shows survival curves for bugs in Debian. You might notice that there are two groups of curves. It turns out that the two groups correspond to two types of severity. Those fixed more quickly are the severity levels considered release critical, and the others are not release critical. And you see down here, they're sort of broken out by the different severities and then how many remain after various numbers of days and their probability of survival. All right. Another problem with using bug data for a distribution like Debian is that some packages have relatively few bugs or may have a high variance for resolution time. So to calculate an estimate of problem resolution for each package, we use Bayesian hierarchical survival analysis of bugs. A Bayesian approach lets us make progressively better estimates as we have more information. A hierarchical or multi-level analysis lets us take a partial pooling approach, making use of what we know about the structure of the data. A survival analysis, as I described, lets us deal with the fact that much of our data is censored, that is, the bug is still open. We make use of the fact that we know that it's survived unsolved for at least some duration, and we can compare across other bugs that have survived for a similar duration. Our analysis is of just under 22,000 packages and the community's track record of dealing with about 500,000 bugs. For our measure of importance, we use Debian's system called popularity cont'd, examining installation rate as reported through opt-in surveys from about 200,000 systems. This is from the PopCon homepage, popularity contest homepage. They call it PopCon, and it shows the number of survey responses from each architecture from 2004 to 2021 on a log2 scale. At the top, this red line here is AMD 64, and this green line here sort of crossing over and then falling below AMD is your i386 architecture. For our case, we used just a single day snapshot of this survey data from July 6th, 2020. Next step, relating quality and importance, we took a rank ordering approach between quality and importance. This is just that idea that the most important component should map to the highest quality, and so on. And our last step in the method, step 5, is to test for deviations. And where the rank orderings of quality and importance diverge substantially, we characterize those packages as misaligned, either overproduced or underproduced. And what we found is that underproduction is significantly widespread in Debian. So this shows the estimated underproduction factor for each package. Because we're taking a Bayesian approach, our estimates are not points but distributions. There's a single color-coded vertical line for each package, indicating the 95% credible interval for our estimate. The sort of orange color here shows those packages where the 95% credible interval crosses 0. This is a conservative estimate of alignment. The right-hand graph has those packages we can credibly say are misaligned. In the green on the left, we have overproduced packages, and in the blue, farthest to the right here, we have the underproduced packages. There are more than 4,000 underproduced packages in Debian out of that 22,000 we looked at. This is all software that may be at risk because of that mismatch between quality and importance. So we've walked through this 5-part method, illustrating it with the Debian case. I'm going to talk a little bit more about what we found from applying this method to Debian. So here's another version of the same data that appeared in the color smear slide. This heat map shows us where those underproduced packages are with respect to usage and quality. The darker colors indicate more packages, and you see there's this concentrated area in black at the lower right. Those are those underproduced packages, the heavily used, low-quality components we're concerned about. And this figure shows the packages with the most severe underproduction issues. Based on our analysis, these are the 30 packages with the greatest underproduction concern. The most extreme example on this chart is GNOME Power Manager for managing power consumption. Not only do serious GNOME Power Manager bugs take a very long time to be fixed, it's widely installed in Debian. Installation-wise, it's in the top 2,000, but for quality rank, it's in the bottom 5. We made 3 observations about these results. First, what we're calling here is this long tail of GUI underproduction. Second, I'll comment on some implications for software engineering research, and then I'll talk a little bit about what implications this work might have for practitioners. All right, so this is that list of the 30 worst that I showed you before. And one observation we had is that 12 of these are part of the windowing system, like GNOME, KDE, and X Windows, and an additional 7 are oriented to desktop uses. Those of us familiar with the early history of GNU Linux as a desktop operating system may not be tremendously surprised by this result. The OS has come a long way since those early days, but perhaps not far enough. And lest you think that these are picky kind of aesthetic issues, if you inspect the bug list of these packages, you'll see many very serious bugs. And ultimately, it doesn't matter what you use a component for. If it takes a system down or opens it to a security attack, you have a problem. So implications for engineering research. This is where I hope we can collaborate as a community. We've demonstrated a method for detecting risk, but there is more to be done using this method, as well as modeling sources of risk and appropriate remediation. We are open to collaborate with others to understand how underproduction can emerge in FLOSS communities and how it can be addressed. Further, there are implications for practitioners in this work. We propose that this line of thinking may be quite useful to development teams prioritizing across their products or managing competing concerns, including not only their own products, but products on which they depend. So if your toolchain, your success, your profits rely on an increasingly neglected component in that free Libre open source software ecosystem, it may be time to invest in improvements to our shared infrastructure. Here also, we are open to collaboration. If you'd like to apply this method to your environment, I invite you to get in touch. For my part, I'm eager to understand more about what drives underproduction, how it emerges over time, and what might mitigate or counter it. Our theme in this presentation has been underproduction, casting light on neglected infrastructure and describing a method to measure the problem. We walked through an example of how that looks in practice. And now we hope that others can use this approach and apply it to understand their projects. We're releasing code and more materials describing this method. The future of our digital infrastructure relies on thoughtful engagement from across the spectrum of computer science and social scientific expertise to understand neglect, identify risks, and mitigate harm. Measuring quality and importance are key to this. So let's continue this conversation. We'd love to talk to you about what we found and how to extend this line of work. Thank you so much.